It is the second marking period, and it is time to get to Unit 5, the relative age of rocks in this unit, entitled Age of the Earth. So in this unit, we're going to start looking at geologic time and how old the Earth is, and while we've seen a lot of the processes that have made the Earth look like it does now, we're going to take a look at how we have gotten to that point. And one of the big things is the big vocab word, and it's the big vocab word, it's the big word, uniformitarianism. And that is the idea that the past can be explained by the current geological processes. So earthquakes are happening today, they've happened the same way in the past. Volcanoes are erupting today, it happened the same way in the past. Same with plate tectonics, seafloor spreading, all that stuff that we've found out is occurring now also occurred in the past. And so all the things, all the geologic processes from the past can be explained by current processes. And due to this, we've come up with the idea that the Earth is 4.6 billion years old, determined by a guy named James Hutton. We'll hear a little bit more about him later. So he's the guy that came up with this idea of uniformitarianism. And what he actually said is that the same forces that change the Earth's surface now worked in the past. And again, that is just a different way of saying uniformitarianism. It's a fun word. You should say it a few times. So when Hutton came up with his idea, a lot of people got quite upset, because at that point in time, people looked to the Bible to figure out how old the Earth was, and guys counted back how many generations there were. As you read through some of the early books in the Bible, it tells you who begat who, or who fathered whom, all the way back to Adam and Eve's time. And then we figured out, we multiplied that by the average life expectancy of a person, and we came up with the Earth being a shade or somewhere near about 6,000 years old. And that's what we agreed on, because that's what our evidence was. What Hutton did is he looked at the rates or the speed of various processes such as erosion and deposition at the end of rivers and lakes and streams, and saw that they took a really long time. So how could we end up with these large structures formed from these erosion and deposition when those processes took so long? All right, one of the things he could look at was like the Grand Canyon. You can see at the walls of the Grand Canyon different layers of rock as you go up. All right, and it looks like this river cut away through the channel all the way down to where it is, and that would take an enormous amount of time. That was some of Mr. Hutton's evidence. So he came up with this idea of relative age. And I mean, it wasn't really a new idea. People can take a look at the relative age of stuff. It's just the age of objects in relation to others. So how old are you, a 9th grade student, maybe an 8th grade student here at McQuaid, relative to me? All right? So you are younger than I am. All right? And that's just relatively speaking. We don't get into any kind of numbers. All right? Relatively speaking, what is the relative age of Mr. Jones and myself? Well, I am younger than Mr. Jones. So that, again, relative age. So one of the things we did is we started looking at the relative ages in rock layers. All right, and we've talked about layers of rock, and we talked about sedimentary rocks. They get laid down in layers called stratification. So we call these layers strata. And it shows the sequence of events that have taken place. And we're going to go through that a little bit more right now. So what we do is we take a look at a layer of rock and we come up with the order in which the rock layered form. All right, and it can be a pretty simple process at times. It can be relatively complex at other times. And what we're looking for is a relative age, which is younger and which is older. All right, so what we're coming up with this is that we know what layer is older than others, what layer is younger than others, but we does not indicate the rock's actual age in years. There are no numbers for the ages. It's all relative. And all of this, we study the layers of sedimentary rocks. So here again are pictures of sedimentary rocks in various places. You can see the different layers, the different lines, and they even look a little bit different in different places, all right? Here's more of a textbooky drawing, all right? You got slanted layers here and other ones, but you can see the different types of rocks exposed at different areas, all right? And when we do is we look at these layers to figure out which layers are younger, which are older. Why are these tilted sideways? What caused them to tilt sideways? And when they tilted, did that happen before or after all these ones on top of it? It's all figuring out how old stuff is in relation to the other stuff. To do all this, we use something called the law of superposition. All right, and it's a fairly common sense type law. All right. A rock layer is older than the layers above it and younger than the layers below it. So think of your locker, all right? And if you started piling stuff up on the first day of your locker and never took stuff out, the stuff that has been in there the longest would be on the bottom. If I had a pile of books in my room, the books on the bottom were the ones that were placed there first. They were relatively have been in their spot longer than the ones above it. And this is because of how sedimentary rock forms. Sedimentary rocks form when new sediments are deposited on top of old sediments. So it's just making layers. Think of when you make your bed, all right? You put the bottom sheet on first. Then you put the first sheet on top of that, and then maybe a blanket, and finally a quilt at the top. Well, the last thing you put on is the thing at the top. You can't put the quilt on top of everything else unless everything else is there first. And so what we end up doing is we look at these layers, we call them strata, and we can also call these layers beds. And the boundary between the two beds, or the two layers, the two strata, are called bedding planes. It's that area when you switch from one layer to the next. What we have here in this picture, here we have 3 layers of rock. A is the oldest because it was there first. B cannot go on top of A unless A already existed. B is in the middle. C is the youngest in this diagram, and here we have some water. Maybe like a shallow ocean or stuff, and skeletons and shells of marine organisms start piling up and settling, and we're getting this limestone right here, all right? And we get in layer C. Well, if we zoom ahead a couple million years or so, layer C stopped, and now we have new sediments on top, new sedimentary rock on top of that limestone. So layer D is younger than layer C. All right, C is younger than B, and B is younger than A. That is the law of superposition. The lower the horizontal layer is, the younger it is. And it goes hand in hand, law of superposition goes hand in hand with this idea of original horizontality. There's a lot of awesome words in this unit. Uniformitarianism, superposition, horizontality. I mean, it's a rapper's paradise right here. So what we got going on is we got scientists knowing that sedimentary rocks generally form in horizontal layers. So if we leave these rocks undisturbed, they will remain horizontal. If I stack up 20 books and leave them and nobody touches them, those books remain horizontal. So we assume that those layers are horizontal and have not been tilted or deformed, which means any deformation, any kind of tilting or bending of the rock had to happen after the rock was there, because you can't bend something that doesn't exist. And these bends and breaks in rock are called unconformities. So it's created when rock layers either are eroded or when they're not deposited for a long period of time. So we see a missing layer. Missing layer. Unconformity. All right, and what happens is movements in the crust will lift up rock layers, expose them to erosion. If it's a thin layer, it can get eroded, and then new sediments get deposited on top. And so now we have these missing layers, and it's a break in the geologic record. All right, so you're going along, layer, layer, layer. Oh, hey, this looks like it's kind of choppy and shouldn't be like that. That is what we would call the unconformity, and then maybe we're missing a layer or so. There are three major types of unconformities. There are the nonconformities, all right, and that is when stratified, which is layered rock, rests upon unlayered or unstratified rock. There's an angular unconformity, all right, and that is tilted. The rocks are at an angle. And then there's the disconformity, and that is when we have rocks deposited on an eroded surface. We'll see some examples coming up. All right, so here's the nonconformity right here. What we got going on. We have these beautiful layers of rock, and then all of a sudden, there's this weird blob of a rock right here. That is a nonconformity. It wasn't laid down in horizontal layers. It's probably not even sedimentary rock. It's probably metamorphic rock or even igneous rock. And so it's a nonconformity. It wasn't laid down in layers. An angular nonconformity, you end up with these angles. Something causes the rock to be tilted. So instead of being nice and horizontal, we have these angles instead. All right, and then this line shows that there was some erosion, and then we have our horizontal layers once again. And finally, the disconformity, we see the eroded area, and then new layers forming on top of that eroded area. The next thing to figure out is the idea of cross-cutting relationships. So that means that a fault or a rock that cuts through other rock is younger than the rock it cuts through. All right? Again, you can't cut through something that's not there. So we already know a fault is a break or a crack in the rock. And we have these other things that cut across rocks called intrusions, which is when masses of magma, igneous rock, magma shoots through some cracks into rock or gets injected into the rock. All right. The big thing to remember, a fault or an intrusion is always younger than the layers it cuts through. Alright, what we got going on this page is we're trying to figure out the ages of these 4 rock layers, this igneous intrusion, and this fault line. Alright, we're going to use cross-cutting relationships, we're going to use original horizontality. Now it says to come up with the oldest to the youngest. But I think sometimes it's a little bit easier to work backwards. So our youngest thing here is let's look at cross-cutting. Do we have something that cuts across everything else? Well, we do. This fault cuts through A, it cuts through B, it cuts through C, cuts through D, and has moved this igneous intrusion. So it had to be the last thing to happen, which means it is the youngest. So the youngest is the fault. Now we have to start thinking. Alright, we have this intrusion that cuts across stuff. It cuts through A, cuts through B, cuts through some of C, but not all of it. So what that means is that the intrusion is younger than C. Alright, but it's not younger than D because D is on top of it, and even some of C is on top of it. Remember, these get laid down in horizontal layers. So this intrusion came up before C finished being laid down. So the next youngest thing on here is layer D, because it is the top layer. Then we have the igneous intrusion. Alright, and that leaves us layers A, B, and C, and they're really easy to tell. A's on the bottom, B's in the middle, C's at the top of those 3 layers. So C has to be younger than B or A because it's on top. And the reason that our intrusion is younger than C, it cuts into C. So it probably came up while C was forming. And that's how easy these relative ages are. So you'll get some more practice in class. If you have any questions on it, please bring them to class as normal. And I hope you have a good night. Thank you.